Hi, my name is Yoon Che, and I will discuss new efficient algorithms for subgraph matching and subgraph search. First, I will provide a brief introduction to the problems. To begin with, let's define the concept of an embedding. Given a query graph Q and a data graph G, an embedding of Q in G is a mapping from the vertices of Q to the vertices of G, with three conditions. First, the mapping is injective, and second, for each query graph vertex U, the label of the corresponding mapped vertex should be the same as the original label of U. And last, for every edge in the query graph, there must be a corresponding edge in the data graph G. In the example, we can identify an embedding of Q represented by bold black lines. Furthermore, we introduced the concept of a partial embedding as the embedding of an induced subgraph of Q. In this slide, we are focusing on two problems. First, given a query graph Q and a data graph G, subgraph matching is the task of finding all embedding of Q in G. In the above example, there are two embeddings M1 and M2. M1 is represented as the bold blue lines, and M2 is represented as the bold red lines. Second, given a query graph Q and a set of data graphs D, subgraph search is the problem of finding data graphs in D that contain Q as a subgraph. For example, in the provided illustration, we can observe that G1 is the data graph containing Q as the subgraph. Now we're going to show an overview of our algorithm. Many efficient algorithms with diverse approaches have been suggested in recent years. However, challenges still remains. Specifically, there is a considerable amount of redundant computation. To address this challenge, we suggest a new algorithm called BICE, which follows the pre-processing enumeration framework. The pre-processing enumeration framework consists of two stages. In the first stage, we use filtering to identify a candidate set CU for each query vertex U, where CU is a subset of VC to which U can be mapped. For subgraph search, if there is an empty CU, we will skip the search. In the example below, given the query graph Q and the data graph G, we'll establish a candidate space in which we will search the candidate space for embeddings. Later, we will provide a detailed explanation of the candidate space. In the second stage, we choose a linear order of the query vertices called matching order and apply backtracking. Our three new techniques are applied in the enumeration stage. We will discuss these three techniques later. In this section, we will discuss candidate space. The candidate space for Q and G consists of the candidate set CU for every query vertex and the edges between candidates. As defined earlier, the candidate set CU is a set of vertices in G to which U can be mapped. Furthermore, an edge exists between candidates if there is an edge between them in the data graph. Creating compact candidate space is important as a compact CS can result in a smaller search space. We adopt the extended diagraph DP method proposed in the previous work to create compact CS. Now I will present the three techniques we propose. Firstly, our initial techniques involves pruning by bipartite matching. Our three techniques are applied within the backtracking framework. Therefore, I will now provide a detailed explanation of the backtracking stage. Given a partial embedding M, a mapped query vertex is referred to as extendable if at least one of its neighbors is already mapped in M. Additionally, the concept of extendable candidate sets denoted as CMU is introduced. If U has no mapped neighbors, then CMU is the same as CU. However, if U has mapped neighbors, CMU consists of the vertices adjacent to the mapped neighbors Ni of U in the candidate space. In the figure A, the gray vertices are already mapped vertices, and the blue vertices are considered extendable vertices. In the figure B, gray candidates represent mapped candidates, and blue candidates are extendable candidates. For example, CMU5 includes V3 and V10. Finally, figure C shows a search tree, where each node represents the last mapping of partial embedding. For example, figure C illustrates the linear mapping history of partial embedding M. Our first method begins with an observation. In the example, it is evident that M2 cannot lead to an embedding since V6 is the only candidate for U7, which is already mapped to U3. Therefore, any mappings made after M2 are redundant computations. To address this issue, we propose a new technique to prune out unnecessary search space by using bipartite matching. To utilize this technique, we need to start with the definition of the candidate bipartite graph BM. For a given query graph Q and a data graph G, the vertices of BM are a combination of VQ and VG. Additionally, there is an edge between U and MU if U is a mapping. Moreover, an edge exists between U and V if V is extendable candidate of U. In the given example, figure B represents the candidate bipartite graph corresponding to the candidate space shown in the figure A. In the figure B, the left side includes the query vertices, while the right side consists of data vertices. Please note that U1 and V1 are connected because U1 is mapped to V1. Furthermore, it's evident that if the cardinality of the maximum bipartite matching in candidate bipartite graph is smaller than the size of the query vertices, a partial embedding M cannot lead to a complete embedding. As a result, M2 can be pruned out in the example. Now I'm going to talk about second technique, pruning by fading set with bipartite matching, which is a technique that prunes out redundant search space in the search space. Figure A displays the candidate space, while figure D represents the search space generated from the candidate space. Let's assume that we return to the partial embedding M after exploring M1 and M2. The red area and green area are the reasons behind the failure to satisfy the maximum bipartite matching condition for M1 and M2 respectively. We observed that U4 was not associated with any failures, as it is absent in both green and red areas. This implies that changing the mapping of U4 will ultimately result in failure during extension, and modifying the mapping of U4 is unnecessary. To avoid redundant computation, we define Fm as a set of vertices relevant to failures and skip visiting a sibling node if the query vertex is not included in Fm. In the example, since U4 is not part of Fm, we can skip searching for a sibling node. For more details on this method, please refer to our paper. Now I will introduce our third technique, cell-wide verification. Cell-wide verification is a technique that reduces the search space of backtracking by utilizing the fact that candidates with the same neighbors form similar subtrees of the search tree. First, we define the cell gamma UV, which is a subset of candidates such that candidates within the same cell share the same neighbors in the candidate space. For instance, in the example provided, V3, V4, V5 are part of the same cell represented by the blue rectangle. As evident in the above example, similar subtree in the search trees are generated regardless of which candidate within the cell is mapping during backtracking. To make the compact search space, we define hypermapping. Hypermapping is a mapping from query vertices to a single cell. Similar to embedding, we define partial embedding, which is a hypermapping of an induced subgraph. For example, we can map U5 into cell V10, V4. Please note that single hyper partial embedding corresponds to several partial embeddings. Search space with hypermapping is more compact since it searches for multiple partial embedding at once. And Cartesian product of hypermapping is the set of homomorphisms. As a result, we select injective mappings from multiple sets generated from Cartesian products, which are actually embeddings. Now I will present experiment result of our algorithm. For performance evaluation, we compared our algorithm BICE with several state-of-art algorithms using various types of query graphs. We conducted experiments on several real-world data sets for subgraph matching with a special focus on Twitter graph, which is a billion-scale graph. Additionally, we performed experiments on 6 real-world data sets for subgraph search. To demonstrate the compression efficiency of cell-wide verification, we calculate the average number of partial embeddings covered by hypermappings generated through cell-wide verification. A higher ratio is preferable as it indicates the simultaneous search of the numerous partial embeddings. We can observe that the ratio is high and it increases as the size of query graphs grows. In terms of query processing time for subgraph search, our algorithm runs 100 times faster than Beck and exhibits a speedup of 1,000 times compared to CFQL. Regarding the query processing time for subgraph matching, our algorithm runs 1,000 times faster than RIFS and rapid match on DBFE. Additionally, our algorithm runs 100 times faster than GQL and Beck. In conclusion, we have presented a novel algorithm equipped with 3 techniques and have demonstrated its performance through extensive evaluation. For details of in-depth discussion on the performance evaluation, please refer to our paper, which includes sensitivity analysis and the performance gain of individual techniques. Thank you for listening.